Hello, my name is Grzegorz Jaśkiewicz and I work in Jutsu Games as research and development lead. And I'm working on an Operator 112 game, but today I would like to tell you about its predecessor, Operator 911. As you might have noticed, 911 is emergency number in United States and 112 is emergency number in Europe. So Operator 911 takes place in the United States and Operator 912 takes place in Europe. In both games, player takes a role of emergency number line operator, where he answers emergency calls, dispatches emergency units to incidents, and manages emergency teams. For example, he buys equipment for a team and assigns vehicles and team members. In a slide, you can see a screenshot from Operator 911 game, where there are units scattered around the city and player dispatches them to various incidents. Score is based on severity of incidents that player failed and succeeded to resolve. So one of the things player valued most in Operator 911 was dialogues that player carries out during emergency calls. Those tend to be very emotional, and some of them are based on real events. Other things that player liked was ability to play on real-world cities around the world. So there are over 200,000 cities to choose from. They are stored on 150 gigabytes of data. So obviously we couldn't just put it to game binary and ship it to players. We have to serve it online. Besides, player uses only a small fraction of this data. So in order to serve the data, we built an online serving infrastructure. Our server serves two types of data, and maps, graphical maps is one of them. Those use Mercator projection, which is pretty common around the internet. For example, Google Maps, Bing, and OpenStreetMaps are using this projection. There is a small difference. Those online mapping services are serving tiled maps, while we serve a single image per city. So there are three types of maps. One is small, which acts as an overview of a city. Player sees such a small image before he or she starts playing on a map. It covers area of 9 × 9 kilometers and is about half of megabyte of data. Other type is a regular map where actual gameplay takes place. It covers playable area and is still 9 × 9 kilometers, but the size is 5 megabytes in this case. Last type is extended map. It also has a 5 megabytes, but covers 4 times much of area. So this is a non-playable area at the border. So this is about 10 megabytes of graphical data player needs to download in order to be able to play on a city he selects. Other type of data we serve is map metadata. This describes a city so that player could play on it. For example, it contains names in different languages, so we could do some localization according to player language. It contains geographical location encoded in latitude-longitude format. This is WGS84 standard. And there are some routing data, which contains a road graph so that ground units could move around the city. This is information about different road, the routing network, information whether some road is one way, etc. And there's also points of interests, like for example, police station, hospitals, or banks. So for example, ambulances are taking injured people to hospitals, criminals are taken to police stations, and banks are occasionally robbed by criminals. So it triggers some incidents player needs to respond to. We have chosen to encode this data in XML format because it's readable, but it consumes a bit much space. We could improve it by compression like zip, but unfortunately haven't done this for historical reasons. So this is additional 4 megabytes of data to download for player. We have also a name search service which serves a little of data because it's only 1 or 5 kilobytes per query, but this is important because we identify cities by a numerical identifier while player enters the city name in his language. So we match those names in different languages using Levenstein, also known as edit distance. If there are multiple cities that match, there is some ambiguity, we provide suggestions so player could narrow down his query further. So now I would like to present the scale of our servings, so you have an idea how much we have to serve each day. On the top, you can see different events which happen at the product life cycle. In the middle, there is amount of data downloads per day. And on the bottom, there is amount of data which was downloaded on some particular day, which corresponds to event which is on the top. So first most crucial event in product's life cycle was the premiere of game. It was very important because it put huge stress on our serving infrastructure. It was the biggest peak and the biggest one so far. We served 1 terabyte of data per day at this point, but it declined over time, and we had the next spike again on a Steam sale, where we reached a point that we were serving 600 gigabytes per day. Then there was a second Steam sale, and then we served 450 gigabytes. Then for a longer time, this was nothing happening, but we were working on a mobile version. And when it was released, we gained 150 additional like residual traffic per day, because we were running a free demo, which was pretty popular, and it gave us additional traffic. So from this now on, we were serving 150 gigabytes per day. Next, we released DLC, and we reached a point when we were serving 300 gigabytes per day. So this was pretty little compared to other Steam sales. And recent Steam sale gave us in total 600 gigabytes. Currently, we're serving 200 gigabytes per day without any significant events to keep the game running. So now I'd like to tell how we constructed our serving infrastructure. First of all, what data do we serve? Where we have taken it from? So there is a project called OpenStreetMaps. People collaborate online. There are over 4 million collaborators which try to create open mapping data under permissive license. So you are free to use as long as you provide those data on request for free. Those collaborators generate something like 3 million change sets a day. you can download all those data, which is encoded on almost 40 gigabytes of raw data in protocol buffer format. Or if you are a fan of XML, you can download 800 gigabytes of XML data. The data set is described by nodes, ways, and relations. So first, nodes. Those are most basic entities you can find in OpenStreetMap data. Those represent single points. They have its own identifier because they could be referenced by some other higher level entities. They have geographical coordinates with latitude and longitude, and tags, which are key value pairs, which form a metadata, describe what a given point is. So for example, traffic signals are such kind of node. So you can see them on the right. They are described by tag with key highway and value traffic signals. There are also more complex entities represented by nodes. For example, a bus stop, which has also a name and a network that it belongs to. More complex type of data that could be found in OpenStreetMaps are ways. So those are basically a series of points. They also have identifier, but they have also a series of references to nodes which form this road. They also have tags, like similarly to nodes. And they could represent, of course, lines, but also the polygons if last node references the same node as a starting point. So those are very common and could be used for various things. For example, buildings. On the right, you could see an example of actual road, which has a name, number of lanes, and what information that this is a one-way road. As an example of polygon, I have shown a forest with a name. So as you can see, naming way could be misleading because ways does not always represent something you could travel along. So most complex type of data is relation. This is a series of way. Each member of relation has its role. So for example, relation could describe a complex polygon. In such case, there is one close way which serves as a boundary, and several closed ways which serve as a whole. On the right, you can see example of such polygon with holes, which is large body of water with islands. So this is obviously polygon with holes. Other usage of the relation is when you have to group different objects which have same metadata. So for example, complex buildings are described this way. Palace of Culture and Science has such a representation, for example. Overpass, OpenStreetMaps has also own software for serving. One of such software pieces is Overpass, which is a database for OpenStreetMaps. So it organizes OpenStreetMaps data. It uses a RAM filling curve to index the data. So this curve starts at point 0, 0 and goes throughout all the plane with just a single numeric index. So this helps to achieve good data locality and results in fewer disk transfers as compared to, for example, MySQL database, which was using 2 indices. So there is some efficiency gain when you're using Overpass. It could import data automatically. So when we were using it, we just put whole planet file onto it, and after 1 day of processing, we have Overpass up and running with serving all the data. It can also run an update loop, which listens for diffs, which are published minutely, hourly, and daily, and it could apply this, so it keeps data in up-to-date state. But we weren't using this because we used caching very extensively in our architecture, so we would need to develop some kind of cache invalidation mechanisms if we decided to use this. We communicated with Overpass with its query language, which allows for bounding box queries. Also, we used queries for specific node types. And as a result, we get data in XML or JSON format. So we were using XML. Other piece of software that we used was Mappertif. So we use it for rendering maps. This is a proprietary software which takes OSM data and output graphical maps. Example of such renderings could be seen on the right. You could parameterize Mappertif with a style sheet. There is an example of a simple rule which tells how to color highways under constructions. Of course, this was more complicated than that, but it should give you an idea in general how it looks like. Mappertif is a Windows application while our servers were running Linux. So to run this, we needed a bit of heavyweight dependencies like Wine, X11 Windows system, and VNC, which is kind of like a remote desktop, just to run this application. For this reason, we couldn't use Amazon Compute Cloud because they didn't allow VNC under the Amazon Linux distribution. So to make Overpass and Mappertif work together, we needed some glue. This glue was done in the form of Java code hosted on Tomcat as servlets. So our code, first it invokes Overpass to get the data. Then it does some additional processing. For example, some points of interest are mandatory for gameplay to start. You need at least one hospital and at least one police station. So if they are known in the data we get from Overpass, Tomcat could virtually add a few such points of interest. Then it passed data to Mappertif, which started rendering maps. And in the meantime, it transformed initial result that it get from Overpass into form understandable by game. So this was working for us in development, but clearly was not ready for production because it took very long time for Mappertif to generate map, almost 30 seconds, and several concurrent requests to Tomcat caused all the RAM to be exhausted and Mappertif crashed. So we decided to improve this a bit by adding a server-side cache on a local file system. Each time Tomcat generated a response, it put it on a local file system cache. So subsequent requests were served from cache without much processing. So we could go with public release with such setup, but we would need 2 terabytes for such a cache. Possibly it would become a bottleneck and we would need some further sharding of such cache. And also we would need large data transfer quotas. I said a moment ago that we served 1 terabyte daily. So this would cost us some significant money. We decided to do something else instead of constructing own serving infrastructure. So this was using a ready-made solution, which is CDN. CDN is a shorthand for content delivery network. This is a system of caches distributed over an internet in different geographical location. So this is optimized for serving content. We have decided to use Amazon CDN, which is called CloudFront. In order to configure CloudFront, we have to create a storage bucket, which is kind of like a network folder, a cloud drive. Then to configure access, which is basically allowed to read for everyone. Then connect to CloudFront, and we could start putting data into the bucket we created. We were doing this once a day by a script which reconciled data from cache, so it could figure out whether some file is already in CDN and only send necessary files. After reconciliation, all files from cache were deleted because they were in CDN. It was almost the thing that we put to our production, but with one difference. We decided to add additional virtual machines. So in case of emergency, that one virtual machine goes down, we have other one which handle traffic. So if you are doing so, like running multiple virtual machines over internet, you need some system for a traffic distribution. So classic way is to do server-side load balancing. In such setup, you add additional server which clients connect to, and it decides which backend system should respond to query. Those systems could be very sophisticated. They could support variable number of servers. They could determine their health. They could make a load balancing decisions based on load for a given server. There is even dedicated software which does that. But we decided to do something far simpler. We decided to do client-side load balancing. So instead of running additional server with load balancing code, we just put load balancing code onto a client. So our client first tries to download a data from CDN. If it's not there, then it falls back to server. It selects one of the servers, map1 or maps2, and it tries to download from server cache. If it's not there, then it tries asking a server to generate a city. Our servers are identified by names in domain naming system, so we have also some small capabilities to influence traffic. For example, we could make those two records points to single machine. So in case of emergency, like one machine not responding, we could direct all the traffic to a single server and start fixing the one that is not working. It also helps when we have some planned maintenance that we need to take one server down and do some maintenance job on it. Also, when you run servers online, you need to know what's going on. Reading player complaints that the game isn't working on a forums is not nice. It's better to act beforehand. So you need some monitoring. This could also give you some value metrics which could be useful to make some business decisions. And it also helps to resolve emergencies. So we used several such solutions. First of them is Amazon Console, which provided data about the CDN usage. So we could read, for example, how much data players download, what is the latency, what is the error rate. So this simply works without any configuration, but it's limited to just 3 months of historical data. Other thing we used was Google Analytics. This is a wide-known solution. It has many integrations. If you are using Unity, there is, for example, assets you could use to instrument code to send some events. If it has no integration for your framework, no problem. It has also HTTP protocol called measurement protocol, so you could send data from basically any system which supports HTTP requests. So we were using this, for example, on a server. But more, we use it on a client to track what players are doing in game, like which dialogue options they select during conversations. On a server, we use this to track performance and also exception traces, which occurred during the server lifetime. This Google Analytics retains full history of data, which is very nice. But despite it has some support for real-time events, neither performance nor exception traces are shown in real time. So we just use it to inspect general trends rather to do some real-time monitoring. And we used a tool for real-time monitoring, which is Datadog. So you need to install an agent which sends matrices to Datadog Cloud, where you could analyze them and they are visualized. So the graph you could see on a slide in a real system is actually updated in a real time. Nice thing is that you could set up alerting. So for example, if disk usage is high, you get notified. So you can act before a problem starts to be severe. Also, those graphs you could see, you could create many dashboards from them. You could mix different kind of widgets, so you could make it suit your need the best. Now I'd like you to tell about few pitfalls that we have while running our servers. One of them was the fact we noticed that some cities are kept being regenerated even if they were in CDN. So what we discovered is that download from CDN may fail. And since we were running client-side load balancing, such load balancer tried to download data from a cache. If it was not there, because it was already sent to CDN. So in such case, it asked Tomcat to generate new data. So it ended up being in cache again, even if client could download it from CDN. And sometimes it couldn't simply download it because internet connection was very slow and it just timed out. So we needed to fix this problem because even if the fraction of such user is small, which large user base, it would cause the cache to fill up prematurely. We fixed it by adding extra CDN check on a server side. So each time the server is asked to generate data, it checks if it's already in CDN. If it is, it downloads it and serves a version from CDN that it downloads. Other problem that we have was players complaining that some cities are very similar in gameplay. So for example, there is London and there is Westminster, which is called city inside a city. It's very close to city center. So you can see those maps are almost identical. They have large overlapping area. So this was by design. This happened because we serve maps which have a fixed size and focus them on a center of a given city. In ideal scenario, we would just serve for a London a bigger map, because London is much bigger than just 9x9 kilometer area. So this isn't a problem by itself. It might be annoying to some of the players, but those overlapping areas looks like a wasted storage, and it prevented us from implementing gameplay on a city districts. We would need much more storage space to support this. So in a sequel of Operator 911, we plan to solve it by serving a tiled maps, similarly as Google Maps, for example. We would construct maps of disjoint tiles rather than to serve a single image per city. Last but not least, I'd like to mention a few security considerations that we had while building our infrastructure. A good rule says that you should choose adequate security measures to value of data that you are protecting and risk of potential security breach. So let's see. We serve no business critical data. We actively optimize our data for download. We serve it for everyone. We accept a server downtime because player still would be able to play a game because some of the data is bundled with game, and there is no real incentive for attacking a server because there is no competition between players. As a result, we had a very few security requirements. We have chosen a mitigation strategy, which was implemented by doing a periodic snapshot. So in case of some serious damage to a server, we could bring it back to running state again by using some of the valid snapshots that we do in the past. We observed during server lifetimes a few malicious activities. Port scanning is pretty frequent. It tries to discover which ports are open, so it tries to conduct some attack automatically. For example, VNC was discovered this way, and many bots tried to do a brute force attack on a password for VNC. But VNC disabled it itself after a few unsuccessful attempts, and sometimes we need it because MapperTiff was using it, and sometimes we needed to reconfigure MapperTiff using VNC. Once there was DOS attack, this is denial of service attack, which was carried out by a script which caused our data to be regenerated. It put much stress on server because it's CPU intensive. But this attack stopped before we took any action, so we couldn't do anything about this. We have also some problems with piracy, but we don't solve this problem on a server side. We have a few client-side heuristics which try to discover whether a version of a game is a pirate or not. And here, pirates cost us money because they don't pay for a game, and we have to pay for a data they download. But as I said, it's not a server-side check. At the end, I'd like to tell you what we're planning to improve in Operator 112. So first thing is that we plan to do a 3D gameplay. So our maps would be 3D with 3D buildings and terrain. For this, we need to expand our metadata, and we couldn't just use XML because it would get bigger and bigger pretty quickly. We need to use some kind of binary format here to be effective. We plan to use mapnik instead of mappertif. So mapnik is software for rendering maps. It's widely used in industry for serving map tiles. We have tested it. It has far better performance. Like it beats mappertif 6 times in terms of speed. It's also run in a batch mode, so we wouldn't need Windows dependencies on our service. So much lighter setup. And as I mentioned before, we plan to serve tiled-based maps, which each map for a city would be constructed from disjoint tiles. So this would allow us to implement gameplay or on arbitrary areas, for example, whole London. This would also require some changes in the gameplay mechanics, because if a playing area gets larger, distances get larger, and player may not even be on time to react on incidents. So strategic placements of a units plays a bigger role than prioritization of incidents that happen. We also plan to add weather conditions, which will be generated based on historical data. And those could affect gameplay, for example, in that way. In a heavy wind, helicopters couldn't fly. It also will affect incidents that are generated. This game will be coming hopefully in 2020. I hope you will see it and enjoy it. So that's all I have prepared for you today. Thank you for your time, and let's move to Q&A session.
So thank you very much, Grzegorz. If you have any question, please come here and ask.
Hi. So I was wondering, did you consider serving vector data rather than bitmaps?
To serve what?
Vector data of all the maps rather than serving bitmaps, then sending vector data to the clients?
Vector. Oh, yes.
Thank you.
Thank you. To be honest, I don't remember. I wasn't at the project since beginning. I just saw graphical maps. Maybe Bartek knows more history about the project.
So, hello, my name is Bartek. I was working with node operator since the beginning. So for your question, if we consider vector maps instead of graphic maps, yes, we did. Actually, we had a version that used vector, client-side generated graphics, but that was far too complex and consuming. This is supposed to be a mobile game, so generating this data on client side would be far too expensive for the CPU. So that's why we switched to maps generated on server side. Anyway, those are still very complex maps, especially when you consider all the kind of ways, ramps, some tunnels, how the water goes. This would be far too complex. For example, OpenStreetMaps is so strangely designed, let's say, that if you would like to display a coast of Baltic Sea, you need to download the whole Baltic Sea border. So that's far too much to generate it on the client side. Okay, thanks.
More questions? So thank you very much, Grzegorz.
Thank you.
And if you haven't downloaded the mobile conference apps, please do so and rate all lectures starting from Grzegorz. Thank you very much.
Thank you. And I think there is also possibility to rate this lecture, so I encourage you to do so. Thank you.